Good afternoon, everyone. Gosh, it's hard to believe that we're together for the final time in this first series of Bite-Sized Corrosion. Thank you so much for joining us on this journey. If you have been with us from the beginning, you will recall that we have spent the past few weeks trying to demystify some of the corrosion and cathodic protection jargon. You are, of course, welcome to watch any or all of our previous sessions on our YouTube channel, having familiarized ourselves with anodes and cathodes, as well as some means of providing cathodic protection, either using sacrificial anodes or perhaps an impressed current system. Last week, Neil left us with the conundrum of stray currents without divulging how to manage them. Okay, Neil, please help us out. What can we do with stray currents?
Thanks, Vanessa. We saw last week that when it comes to stray currents, we have a number of options in order to endeavor to either control them or manage them. We know that controlling stray currents is extremely difficult. If you think about the power that is represented by those locos, the stray current that emanates from that source cannot really be controlled. All we can do is try and ensure that the currents that are there do not cause damage. And we do that by means of cathodic protection. We saw that we have a relatively small power system which has to compete with the power from these locomotives, for example, which deliver the current to the railways. And equally, when we looked at the sun, the power of the sun is infinite compared to what we have available. So how do we deal with our stray currents? The terms that we mentioned last week can be defined as natural drainage units, forced drainage units, transformer rectifier units, and then these operations are monitored using remote monitoring units. These are all somewhat of a mouthful, and so we tend to use the acronyms of NDU, FDU, TRU, and RMU. And really what these are different types of electrical systems which we can use. Now, we looked at this diagram, and between points B on the pipeline and A on the rail system, which are electrical locations, we can see that there are a number of different options in terms of the type of electrical equipment that we can install. We very rarely put in a direct bond because the danger of a direct bond is that the current may be reversed and actually flow into the pipeline. And we saw that current that flows in has to flow out somewhere else. And so we could be making the problem worse. So between A and B, we can either put a natural drainage unit, which means that it is a simple diode, or as some people call it, a reverse current switch, which conducts current only in one direction, and therefore the current drains back to the source. Or we can add a power unit to that and force the current to flow back to the rail. And we can actually make that unit somewhat more complex, and we can include an electronic control circuit, which then controls the amount of current that is returned to the rail. So if we have the simple situation, as we are showing here, where the stray current is returning to the rail at a point close to the traction substation, then the rail at that point should be negative, and we can control the direction of the stray currents using what we term a natural drainage bond. So this natural drainage bond is a relatively small device housed in a secure location and then connected to the rail in order to drain the current back to the rail. That is represented by a single diode in our electrical connection. But you can see from this diagram that the rail has resistance, the pipe has resistance, the rail and the pipe may not actually be in the same geographical vicinity. So what do we do in that situation? Here is an example of a rail which is not running negative. And if it's not running negative, then the natural drainage unit will not work because a diode always conducts current in one direction, and that is from positive towards negative. So if the rail is more positive than the pipe, a natural drainage unit is not going to work. There may be requirements to drain current back to the rail, even when the rail is not negative with respect to earth. And in that situation, we can use what is known as a forced drainage unit. In other words, we've incorporated a power supply into the connection back to the rail. And this unit is what we have in this diagram. On the left-hand side here is the power unit. On the right-hand side over here, we saw that there's a rail, and there is in fact about a 200-meter long cable going from the rail back to the pipeline, or rather the other way around. We tend not to use forced drainage units because they can cause more problems than they solve. We also have the situation where the pipeline is nowhere near the rail. In this particular case, we saw that the pipeline was corroding over here, and the rail was something like 7 kilometers away. Now, you cannot lay a cable 7 kilometers across the country in order to drain current back to the rail. So in a situation like that, we install a normal rectifier. So this is an example of a rectifier located in the open country, where the ground bed, which is this section over here, can discharge the current back to a relatively low resistance path, such as that dry riverbed we saw in the previous slide, and the current can then find its way back to the rail through the geographical feature. One of the problems of stray current control or stray current mitigation is how do you actually determine how much current is needed. If we are going to protect the pipe when it is sitting at plus 0.2 of a volt, we need relatively little current. But when the pipe is sitting up here at 1.5 to 2 volts positive, we need a lot more current. And if you don't adjust the output of the system in order to cater for these different scenarios, you can either overprotect or inadequately protect the system. So what sort of control do we have? The simplest control, which is something that we hardly use in stray current situations, is that of a tapped transformer. So this gives us a constant output voltage. And here you can see an example of a system that is installed. There is actually a rail in the background, although you can't see it hiding behind these concrete bunkers. And here you can see that we have a fairly heavy rectifier, which is pushing current back to the rail. Probably the most common control system is that using thyristors. We're not going to go into the electrical circuitry of this, but here's a typical example of a thyristor controlled unit, where you can see we have output meters which show us what is going on. The pipeline potentials are shown by these displays, and there are a number of indicator lights. There are various different control modes, and the output is adjusted by means of a simple potentiometer. An alternative to thyristors is what is known as a saturable core reactor, also known as a magnetic amplifier, which gives us a constant current characteristic. These units find quite a lot of application, but they can also be somewhat problematical. The power supply of the future is undoubtedly the switch mode power supply. It is totally electronic. It can provide us with various control modes. So the first control mode is constant output voltage, such as we get from a tapped transformer. The output voltage of the transformer rectifier unit is constant irrespective of the current. It will then provide you with protection. The challenge, of course, is that if you set this to the highest level, you're likely to overdrive the pipeline during low current or low interference states, and vice versa. The constant output current characteristic gives us a constant current irrespective of the resistance of the load. This is particularly useful when we have climatic or seasonal changes, and the output current of the unit then remains constant irrespective of the driving voltage that is required. This is an internal feedback control system that is inherent in the power supply itself. Perhaps the most common control system that is used for stray current control is that of constant pipeline potential. In that case, we actually measure the pipeline potential with regard to soil. Here's a typical instrument that is used to measure it when you're in the field, and it is measured with respect to a standard reference electrode. In this case, we're doing a portable test out in the field and have used a temporary electrode which is buried in the soil. With the advent of these switch mode power supplies and digital controls and so on, it is possible to apply a number of other control modes. For example, we can switch the cathodic protection system off and measure the resultant IR free potential. We can switch a coupon off and measure its potential. We can even monitor the potential at a point that is some distance from the rectifier and control the output of the rectifier based on that potential. One of the challenges, of course, with these electronic components is that they do tend to be somewhat sensitive to operating conditions. And we've all seen the sort of storms that we get in South Africa in particular, but they happen all over the world. And so these electronic devices are somewhat susceptible to failure due to the effect of lightning. And there is an example of a fairly complex digital control system that could be used for a pipeline network. Where do we put this control system for stray currents? We can talk about the factors that reflect the location of a stray current unit. The first one is location, the second one is location, and the third one is location. The current has to go back to its source, and that source is not going to move. This is a fixed installation which is installed with the rail, and that's where the current is going to go back to. And so you have to have your drainage unit in the right place in order to conduct the current back to that source, whether it is a direct rail bond or a bond through a geographical feature. There is an example of a situation where a number of attempts were made to protect this green pipeline. As you can see, it crosses the purple rail and the yellow rail at various locations. And attempts were made to protect it by putting drainage bonds at the crossings. Hundreds of amps were drained from the pipe back to the rail. None of them worked because the current actually wanted to go through these wetlands there and there back to a traction substation that was located over here, further downstream. And at the end of the day, a relatively small rectifier was installed at this location here in order to conduct the current back to its preferred route and thereby prevent this pipeline from corroding. Something that happened in the course of this pipeline's history is that some years after the initial system was installed, the railway operator installed a new traction substation at this location over here, which changed the stray current pattern completely. So once you've got a system in and working, don't rest on your laurels and think that it is going to continue working forever, because circumstances do change. How do we know what is going on? Well, that's where that RMU comes in, the remote monitoring unit. Here is an example of some potentials that have been measured at a rail. You can install a monitoring cabinet out in the middle of nowhere, and then you've got to send somebody out to go and work on it and maintain it, measure it, and so on. Or we can install permanent installations, such as permanent reference electrodes. These are different types: copper, silver, zinc. And these are then used in conjunction with monitoring equipment to measure the operating potential of the pipeline and send that data back either to control a rectifier or to send it back to a central database where the operator can evaluate what is going on. Here is an example of the screen of a control system where the cathodic protection system then has all its parameters demonstrated here. together with the various electrodes, and he's able to check the operation of that unit at any time. I cannot do it now because I don't have permission, but I could log into a rectifier that's many hundreds of kilometers away and check its operation and show you what is going on. So having looked at some of the things that are used to protect pipelines, we need to know when we construct a pipeline that it is what we call CP ready. Is it ready to have cathodic protection installed and operated on an economic basis? Perhaps the most important aspect, the pipeline itself needs to be electrically continuous. Where there are valves in line, these valves need to be bonded over, because if you have an electrical break in a system, you can actually set up interference currents across these electrical breaks. We need to make sure that the pipeline has been well wrapped. This provides the electrical insulation between the pipeline and the environment. In this case, we have a bitumen coating on the pipeline and an epoxy coating on the special that you can see in the center of the photograph. That special subsequently gets cast into concrete in order to protect it. The pipeline needs to be isolated, but now, hang on, I just said it needs to be continuous. Now it needs to be isolated. Well, the pipeline as a unit needs to be continuous, but it needs to be electrically isolated from everything else. And we do this by installing what we call insulating flange kits. Here's a photograph of what you can see of a kit on a flange, and there you can see an insulating washer. What you cannot see is that on the stud going through here is an insulating sleeve, and in between the two flanges is an insulating gasket. This whole system is then protected by a surge protection unit, which is located across the top. It's a spark gap, which allows transients from lightning or switching surges to be safely conducted. Where do we install these devices? Firstly, pump stations. Pump stations have huge pumps and earthing systems, all of which would drain the current from a cathodic protection system. We need to isolate our pipelines from reservoirs. Reservoirs are generally large concrete structures. These are reinforced concrete structures, which again would drain all the cathodic protection current if the pipeline was in contact with the steel reinforcing. This is in fact a major challenge with pipeline construction. We've had a couple of instances where a random connection between a piece of reinforcing and the pipeline has caused major hassles because it has drained the current from the pipeline and resulted in a lot of expense to try and find the drainage point inside this reinforced concrete. These have been water pipelines. Gas and oil pipelines have nothing different. We just have a different name for them. They are called AGIS, or above ground installations. And as you can see, there's a lot of bare steel around, a lot of earthing, a lot of foundations, and a lot of electrical equipment, all of which has to be earthed, and therefore we do not want to be in contact with this. If you have a look here in the middle of the photograph, you can see all the earth connections going to a central earth bar, and that goes to a huge earth mat, which is there for electrical protection. Water pipelines have flow meters, and this is another perennial problem that we face because the flow meters sometimes do not get installed with the correct insulation. Again, you can see the heavy copper earthing cable that is necessary for the flow meter, and that goes off to the plant earth, and we need to make sure that the pipeline is isolated. And you can actually see the isolation kits or insulating kits, whichever you like to call them, on each side. And in this photograph, you can in fact see the insulating gasket that goes between the two flanges. A relatively recent challenge that has come up is that of electrical actuators on valves. At one stage, it was possible to isolate these electrically from the valve structure or the valve body, but manufacturing principles have changed, and these are now integral with the valves. And it has meant that in order to isolate this electrical device from the system, we actually have to insulate the entire valve from the pipeline. As I mentioned, civil structures, reinforcing must be kept well clear of pipelines before the walls are cast. Otherwise, we'll end up with these challenges. So we have a pipeline. It's been properly constructed. We have to install monitoring facilities in order to be able to monitor that pipeline once the cathodic protection is operational. That is kind of the end of this introductory series. And in case you thought we'd given you a lot of acronyms, just a word of warning, there's lots more to come. And we hope that you will join us next year when we continue to present these bite-sized corrosion conversations.
Thanks so much, Neil. Just to add my 2 cents worth, that getting our pipelines and structures ready for cathodic protection, actually thinking about corrosion during construction, really does go a long way to ensuring that corrosion control remains a relatively painless effect for everyone. Just related to test posts or test points, if we can just have a little chat about them, Neil. There seem to be some differing perspectives regarding the frequency of test points along a pipeline. What are your thoughts?
Well, it does depend on the type of pipeline. If we're talking water pipelines, we have valve chambers typically every 500 meters, and these form very convenient electrical test points for pipelines. Those acronyms that I threw up on the screen at the end there relate to a number of different survey techniques, some of which require connection to the pipeline, and then you walk over the top of the pipeline in order to evaluate what's actually going on, in order to find perhaps coating and wrapping defects or interference situations or whatever other problems might occur. And it's convenient to be able to connect into something that's relatively close. Gas and oil lines don't have valve chambers every 500 meters. They typically only have block valves every maybe 5 or 10 kilometers. So that leaves us with a lot of pipe that does not have a contact point. And in that situation, typically the maximum distance is about 2 kilometers. And test posts should be located not so much based on distance, but on geographical features. So for example, you would install test posts at river crossings and road crossings and foreign pipeline crossings and proximity to electrical overhead power lines, for example.
I do think that we need to remember that it isn't a one system fits all, but that each pipeline does need to be considered within its own constraints and its own merit. And I think sometimes we tend to want to cookie cutter, or we've had experience on one pipeline and we try and take that out to the next. So thanks for those comments. Just before we end this series, I have a couple of closing comments, if I may. The first one is that if these discussions have stimulated your interest and you would like to find out a little more, we will be launching our CP 101 course on our virtual platform in the new year. Now, this course is a little more in-depth than these bite-sized conversations have been, and it is also CPD accredited, so you can go through it at your own pace. We will send out details to our mailing list and via social media as soon as it does go live. And then there's nothing left to say that until we meet again, we wish you a very blessed Christmas, a well-earned break from this very chaotic year, and let's hope 2021 is a much better year for everyone. So thank you.